probability, just a basic introduction, and then and we'll go from there. So probability concerns itself with the likelihood of a particular event happening. Okay? An event is an outcome or a set of outcomes of a random phenomenon. That's what that is. So let's start with an example. So suppose you were going to roll 2 fair dice. Okay? And you're going to record the results. And then you could ask all kinds of questions. So the first thing you could do, if you wanted to in this kind of a problem, is create what's called the sample space. And the sample space is a list of all possible outcomes. In every problem, they're a little bit different. Okay? So in this case, the sample space is not too big. We're going to write it out. So what could happen? The first die could land on a 1, and the second die could land on a 1. Right? Or we could say the first die lands on a 1 and the second die lands on a 2. First die 1, second die 3, and so forth. So these are all possibilities. Right? Now if we think about the first die not landing on 1, what else could it have landed on? Well, the first die might have landed on 2 instead. So you could end up with these possibilities. Let's be clear on what they mean. This possibility means first die is a 2, second die is a 1, whereas that possibility means first die is a 1, second die is a 2. Okay? So we're just going to keep listing all the possibilities. Now, sort of a fun question to think about before you even start is how many possibilities there are going to be, right? When you think about it, the first die has 6 possibilities for outcomes. The second die has another 6 possibilities for outcomes. There should be 6 times 6 total possibilities. So I'm going to have to make these a little bit more compact. 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. We'll have 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. And what else can we have? 5, 1, and so forth. So we'll just keep listing these. What you're going to see is this is time well spent, because once I start to ask you some probability questions, you'll literally just be able to look through the sample space and see what the answer is. Okay? So here are all your possibilities. List of all possible outcomes. It's called the sample space. Okay. Now, the next thing we're going to do is talk about an event. An event is a random phenomenon. It's an outcome or a set of outcomes that satisfy a certain condition. So maybe I'm going to say to you, find the probability of the event that both numbers are even. Okay, or both die or show even numbers. Okay, so the event is both die showing an even number, and P means find the probability of that event. Probability is always the number of ways the event can happen over the number of total outcomes, or the number in the sample space. So the denominator has to be 36 because there's 36 possible outcomes. And then we just got to count up where both numbers are even. That's sort of a fun thing to do. You'll notice this whole first row here, none of the first column, I should say, none of those numbers will work because they all have a die that landed on a 1, right? So we can get rid of those. We can get rid of that row, or that column, I should say, and that column. And then we'll just look around and we'll see. All right, there's 2 evens, 2 evens, 2 evens. There's 3 there. There's 3 more here and 3 more here. It's a total of 9 outcomes that are part of this event out of 36 total possible outcomes. Not bad. And we could ask all kinds of questions. We can say, find the probability that we have a sum of 7. So that means the 2 die add up to 7. All right, so let's go look into our sample space and see if we can't figure that out. Well, if we look in the first column, the only pair that does it is right here, 1, 6. Right? Okay. Then we go to the next column. Here's the 2, 5. The 2, 6 is going to be too big. 2, 4 is going to be too small. So 2, 5 works. 3, 4 works. 4, 3 works. 5, 2 works. And 6, 1 works. So there are 6 pairs that satisfy that event. 6 out of 36. All right, so you can go on and we can ask a whole bunch of questions. There's other ways to represent sample space. You see I just sort of wrote out the pairs here. What I could have done instead, and sometimes it's useful, is to create something called a tree diagram. Oop, hold on a second. And the tree diagram is a way to list all possible outcomes. So let's say we're going to do the following. We're going to toss a fair coin and roll a fair die. You'll notice I'm making a big deal of using the word fair. What this means is that this is a die that when you roll it, the probability of getting any one of the numbers on the die is the same. So the probability of the die being rolled and landing on 5 is the same as the probability of the die being rolled and landing on any other number. All right, the same thing with the coin. It comes up heads or tails, equally likely. Okay, so we can make a tree diagram to list this. Here's what we can do. We could think of tossing the coin first. So if we toss the coin, it can land on heads or it can land on tails. And then after tossing the coin, we could then roll the die. So here's how you think of it. If we had tossed the coin and it landed on heads, and then we can roll the die, it could come up with any one of 6 possible outcomes. Okay? 1, 2, 3, 4, 5, 6. There you go. And now you literally can read off what the different possibilities are. Right? This first right here and here is saying that we got a head on the coin and a 1 on the die. And then this one says we got a head on the coin and a 2 on the die, and so forth. Down here, this pair means that we got a tail on the coin and a 3 on the die. Tail on the coin and the 2 on the die, and so forth. You can list all your possible outcomes. And you can ask other kinds of probability questions. Okay. That said, the tree diagrams are not always practical. Okay? And sometimes it's not even practical to write out something like this. So for example, suppose we were going to choose 2 cards from a deck of 52 cards, and we'll say with replacement. So the words with replacement are kind of important here. With replacement means that you pick the card, you look at it. Let's say you picked the king the first time, or the king of hearts. You looked at it. Then you put it back in the deck, you shuffled the deck again, and you picked another card. Okay? So when we give this some thought, we realize that the first time we go to pick a card, there's lots of possibilities, right? There's 1, 2, 3, 4, 5. Uh-oh. There's going to be 52 branches. Okay? Got that? And then, if the first card I picked, right? Let's say we'll start with the 2 of hearts, right? Then, after picking the 2 of hearts, the second time I go to pick a card, I'd have another 52 branches over here coming off of that. So you can see immediately this would not be practical to try and write out. You'd have way too many branches to deal with. Well, it's with replacement. So with replacement means that we put the card back and chose again. So that's why it's 52 branches. If this had said without replacement, And then what would change is this number of branches, instead of being 52, would only be 51 because you couldn't pick the same card again. You would have taken the card out, held on to it, and then went back into the deck for another card. So let's try and use sample spaces to answer questions. Suppose you're gonna toss 4 fair coins. And what I'm going to ask you for is to find the probability that you get at least 2 tails. Okay? So that's the question. Now we can write this in a more compact form. You should use this notation when possible. Probability at least 2 tails. That's how we can write it. All right, so make a sample space and try and answer that. So before you attempt to even list the sample space, sometimes it's helpful to try and figure out how many possibilities there are going to be. And if you think about it, we're picking a coin 4 times, so we're doing 4 actions. And we have to think about what the outcome can be for each of those 4 actions. So each time I flip a coin, I have a possibility of heads or tails. So it's 2 outcomes, right? So after tossing the first coin, I have 2 possible outcomes. Then I go to toss another coin, that's another 2 possible outcomes. The third coin has 2 possible outcomes, and the fourth coin has 2 possible outcomes. Well, if I multiply these all together, I get 16. And that means that we have 16 possible outcomes in total. That idea that if you have a series of events that can happen in a certain number of ways, you just multiply the number of ways together is called the multiplication principle. Okay, you've learned about that in the past. So 16 possible outcomes. Now we can list them or we can make a tree diagram. I'm inclined to make a tree diagram for this problem. So here we go. We've got heads or tails for the first coin. Then after tossing the first coin, the second coin could be heads or tails. Heads or tails. Then the third coin could also be heads or tails, but that's coming off each other of these branches. And then we're almost done. You can see now at this point we have 8 possibilities because the last column has 8 items in it. And then lastly, each one of these could have heads or tails come afterwards. Okay. Keep in mind, this problem could have been done using simulations if we wanted to. But what I'm trying to do today is show you how to calculate the theoretical probability. And we could model this using a simulation and see how close we got. It might be neat to try just to see how well we do. All right, now let's keep in mind what our goal was. Our probability that we're interested in is the probability of getting at least 2 tails. So if you want, you can start to write out the sample space. If we follow this first branch all the way up, we have heads, 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 heads. Okay? That would not be considered a success because we wanted the probability of at least 2 tails. Right? Suppose you went this way. You'd have heads, 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 tails. Heads, 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 tails. And you just kind of walk through the tree to get your answers. The next one's going to be heads, heads, tails, heads, 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 tails, tails. Here's your first success right here. That's at least 2 tails. All right. Let's go down here. We have heads, tails, heads, 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 tails, heads, tails. There's another success. Okay? Then you have heads, tails, tails, heads, and then heads, tails, tails, tails. There's 2 more successes. Keep in mind what the word at least means. At least means you got to have 2 or more. Okay? And now you're just about ready here. Here you're going to have tails, heads, heads, heads. And that's not a success. And then you have tails, heads, heads, tails. That is a success. Okay, now if we think about the rest of them, let's just do them quickly now. That's a success, that branch. This is a success. And then this whole bottom branch, all of these 4 possibilities have to work because they all start off with tails, tails. You get 2 tails right away. So you can sort of just check off those last 4 quickly. 1, 2, 3, 4. can count up the check marks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it looks like we have 11 possibilities that make us happy out of a total of 16 possibilities. So there's our probability. Okay? Now, we could have simulated this. And my promise to you is if you simulate it enough times, the probability you get should be very close to 11/16. So let's think about what we could do in our random number generator calculator, right, to simulate tossing 4 coins. The goal is going to be to try and simulate this using a random number generator. So let's suppose someone told us, hey, use randint 1, 2, 4. So let me comment first and say, this is going to work provided we can interpret it correctly, right? So what we're going to do is we're going to let 1 equal heads and 2 equal tails. And then what this thing is doing is that we're choosing 4 random integers between 1 and 2 inclusive. Okay? And let's do an example. Let's actually go to the calculator and see what happens. So we'll start our trials below. So here we go. We clear here. We press math. Go to the left. Probability. Number 5. That's randint 1, 2, 4. Close parenthesis. Enter. Here's our first simulation of throwing 4 coins at one time. And if we do that, we get 1, 1, 2. So let's make a note of that. This is our trials, right? Here's trial number, and we'll say what the outcome was. So trial number 1 had an outcome of 1, 1, 2. Would this be considered a success in our problem? Okay, this is 3 heads and 1 tail, so this would be considered a failure, actually. Remember, we're looking for the probability of getting at least 2 heads. So we made a chart over here with success and failure. Our first trial says we had a failure. Okay, so let's go back to the calculator. Right, because we wanted at least 2 tails. We hit enter. Here we go. We've got 1, 2, 2, 2. So here's trial number 2. We got 1, 2, 2, 2. That's a success. We got at least 2 tails. So what we need to do now is quite a few more of these to sort of see what's happening. So let's hit enter one more time. Okay, and then we've got 1, 1, 2, 2. So trial number 3 gave us 1, 1, 2, 2. That is a success. We had 2 tails. Let's do a whole bunch more trials. Go ahead. So we got a success and a failure. Okay. Success and a failure. 2 failures. 2 successes. 1 and 1. Success and a fail. Okay. 2 successes. Oh, sorry, my bad. I said 2 successes, put them in the wrong spot there. 2 successes. Okay. Success and fail. Success, fail. 2 successes. Success, fail. Okay. 2 successes. Success and fail. Okay. So that's many trials. And what I'm claiming is that this answer should end up being close to 11/16, which was the theoretical probability we got by using the tree diagram. So here we go. We got 1, 2, 3, 4, 5. So that's 25, 28 out of 28 plus another 11. So that looks like 28 out of 39. Let's make sure I didn't make any mistakes there. So, okay, so 11 out of 16 is 0.68, or about. And what's this? And this is about 0.72. So you notice this is pretty close. But you sort of see the disadvantage of simulations. Simulations don't give you the exact probability until you've done many, many trials. Now, here's sort of a promise to you. There's something called the law of large numbers, and with the law of large numbers guarantees lots of things, but one thing it guarantees is this, that after many, many, many trials, this probability, which is referred to as an empirical probability, empirical meaning you got it by doing a simulation or some kind of experiment or collecting data, this empirical probability will get very close to the theoretical probability. That's what the law of large numbers says. As the number of trials increases, the empirical probability will get closer and closer to the theoretical probability. So that's sort of your introduction to probability.